next speaker is William Giarè.
Thank you. In the next 20 minutes or so, I would like to discuss if and to what extent the Hubble tension can represent an element of uncertainty in our understanding of cosmological inflation. You know that we introduced cosmological inflation in the standard model of cosmology to fix initial conditions. Thanks to inflation, we can explain why the universe is flat today and the high level of homogeneity that we observe in the cosmic microwave background. In this talk, I will focus on the simplest scenarios from which we can get inflation. These models are known as single-field slow-roll inflation. The reason is that we have one single scalar field, and all the models are characterized by the fact that the scalar field will undergo a phase of slow-roll evolution on the potential. This requirement can be formalized in terms of the slow-roll conditions, or if you want, in terms of the slow-roll parameters, epsilon and eta. These two parameters will be very important for the following discussion. And you see that both of them contains information about the inflationary potential and its derivatives, and both of them are constrained, must be much smaller than 1 during inflation. However, the slow-roll conditions do not fix the shape of the inflationary potential. We can have many potentials from which we can get single-field slow-roll inflation. So the question is, how can we move forward in our understanding of the inflationary potential? Well, we can do that thanks to the observations of the cosmic microwave background. In particular, we measure temperature and polarization anisotropies in the cosmic microwave background. Here you can see the temperature fluctuations measured by the Planck satellite. You see that CMB photons show differences in temperature of a few hundred microkelvin, and we believe these temperature fluctuations to originate during inflation. Essentially, the evolution of the scalar field on the potential will not be classical. It will undergo some quantum fluctuations. These quantum fluctuations are pushed on super-horizon scales by the fast expansion of the universe. They will re-enter the observable universe during radiation and matter-dominated epoch. They will source fluctuations in the energy density of the universe that we believe are responsible for the temperature fluctuations we measure in the CMB. However, another prediction of inflation is the existence of a stochastic background of gravitational waves. Essentially, during inflation, any degrees of freedom will be quantum mechanically excited. So we expect fluctuations in the metric tensor that are responsible for a stochastic background of gravitational waves that, as we shall see, will imprint the cosmic microwave background polarization as well. Now, if we work in the framework of single-field slow-roll inflation, we can compute the primordial spectra of both scalar and tensor perturbations. And we can adopt power law parameterizations that are characterized by an amplitude, in the scalar case, an amplitude AS, and a scalar spectral index, NS. Similarly, in the tensor case, we have a tensor amplitude that we parameterize in terms of the so-called tensor-to-scalar ratio R, and a tensor tilt, NT. Now, again, within single-field slow-roll inflation, we can relate the spectral index, both for scalar and tensor perturbations, to essentially the slow-roll parameters epsilon and eta that contains information about the inflationary potential. This is very important because now we can use CMB data to constrain the inflationary parameters, and from the constraints on the inflationary parameters, we can derive information about the model of inflation. So what data can we use? We can use the data released by the Planck collaboration. Planck is measuring very well the spectrum of temperature anisotropies, the TT spectrum, the spectrum of E-modes polarization, the EE spectrum, and the cross-spectrum between temperature and E-mode polarization. In addition, we have also CMB lensing. Both scalar and tensor modes produced during inflation will contribute in these three spectra. However, if we compare the contribution arising from scalar modes with the contribution arising from tensor modes, you see that in all the three spectra measured by Planck, scalar modes are always dominant over tensor modes. However, we are lucky enough because we have a range of multiples between 2 and say 100, where in the spectrum of B-modes polarization, the signal can be dominated by tensor mode. Therefore, if we aim to study inflation and achieve the highest possible level of constraining power on primordial gravitational waves, Planck is not enough. We also need an experiment that is measuring B-modes polarization. And so far, the most precise measurements of B-modes polarization at the scales of interest for inflation are released by the BICEP Keck collaboration. This experiment is working in the South Pole, and they are collecting very precise data on B-modes polarization. So when we combine together Planck and BICEP data, we can perform a joint analysis, and we find the results that are largely known in the literature. We can measure the spectral index of scalar perturbations. It is different from one at more than 8.5 standard deviations. This is considered the most important indirect evidence for inflation, because essentially in any single or in most single field models of inflation, you expect an S to be different from one because of the dynamics of the scalar field. However, we do not measure the tensor amplitude. We do not measure the amplitude of primordial gravitational waves. We have just an upper limit on the tensor to scalar ratio. Within the single field Lorentz inflation paradigm, we can translate these constraints into constraints on these inflationary parameters epsilon and eta. You see that we don't measure epsilon. We have an upper limit on epsilon because we do not measure the amplitude of primordial gravitational waves. On the other hand, we do measure eta to be negative and different from 0 at high statistical significance. These constraints are very, very important. First of all, because they set a hierarchy between these Lorentz parameters. You see that in absolute value, eta is measured to be much larger than epsilon. And secondly, because these constraints limit a lot our freedom in choosing models of inflation. Now, if you give me a potential, I can compute epsilon and eta, and if your model falls within these probability contours, then it's in agreement with data. If your model falls outside these probability contours, then it's ruled out by data. Along the years, a few well-motivated models of inflation emerged to explain this data. And in particular, Starobinsky inflation is one of the best-fitting models. In Starobinsky inflation, we can obtain inflation in modified gravity. We essentially add this square-Ricci scalar in the effective gravitational action. And the model predicts some relation for the spectral index and the tensor amplitude. And in particular, you see that the spectral index and the tensor amplitude can be both related to the number of e-folds of expansion from the horizon exit to the end of inflation. Now, if we work within the same assumption made by the Planck collaboration in the paper on inflation, in general, one can consider this number to range between 50 and 70. However, I will say that in realistic realization of Starobinsky inflation, this range can be further narrowed down to 55, 60 e-folds of inflation. Anyway, when we test these predictions against data, again, Starobinsky inflation emerges as one of the best-fitting models, and you see that there is a spectacular agreement between these predictions and current data. However, again, we do not measure primordial gravitational waves, so all future experiments, all future CMB experiments, or at least most of them, are designed to reach a precision on B-mode polarization on primordial gravitational waves that will be enough to confirm or rule out Starobinsky inflation and models similar to Starobinsky inflation. I will say this is more or less the state of the art in terms of constraints on inflation and models of inflation. But now I would like to address to your attention a few elements that may question these results. And in particular, you know that in cosmology we are facing a good number of problems. The most important one is the Hubble tension. We all know about the Hubble tension, so we'll go very quickly here. The Hubble tension essentially refers to a disagreement at the level of 5 standard deviation between the value of the Hubble parameter that we can measure with type 1a supernovae, as done by the Schuss collaboration, and the value that we can extract from CMB data once we assume a model of cosmology, and in particular the ΛCDM model of cosmology. However, the Hubble tension is more than that. We have many estimates of the Hubble parameter based on early time probes, and most of them are scattered around the value measured by Planck, as well as we have many probes, many estimates of the Hubble parameter based on local universe probes, and the vast majority are clustered or scattered around the value measured by Schuss. So if we look at this plot, it looks like there is a gap in our understanding of the early universe and the late-time universe. And this may be the reason, this is the reason why the Hubble tension may be pointing towards new physics beyond the standard model of cosmology. And in this regard, we need to take in mind that the value of the Hubble parameter we measure from CMB data is intrinsically model dependent. We need to assume a model of cosmology to extract H0 from the CMB. How can we extract H0 from the CMB? In the CMB, we measure the angular power spectra. From the angular power spectra, we can extract some cosmic parameters with reduced level of model dependence. In particular, we can measure the angular sides of the sound horizon, θs, from the position of the acoustic peaks. If we change theta, we shift the position of the peaks. We can measure the baryon energy density, omega baryon h squared. If we change this parameter, for instance, if we increase this parameter, we increase the amplitude of the first peak, we decrease the amplitude of the second one, and so on and so forth. So from the relative amplitude, you can measure this quantity. Finally, we can also measure the cold dark matter energy density from the absolute amplitude of the peaks. If we change omega ch squared, we move up and down the acoustic peaks. However, once we have measured these three parameters, we need to assume a model to describe the expansion history of the universe from soon after inflation all the way up to recombination, because we need to compute a very important scale, which is the sound horizon. And you see that the sound horizon is defined as the integral of the baryon photon sound speed over the expansion rate of the universe from soon after inflation until recombination. Once we know the sound horizon, we know the angular diameter distance from the CMB, which is the value of the sound horizon divided the angular scale of the horizon. But then we need to assume a model to describe the expansion of the universe after recombination. Once I know how the universe expands after recombination, I can finally extract H0 from the CMB data. So you see that here model dependence appears twice at least, when we compute the sound horizon and we are sensitive to physics before recombination, and when we compute H0 from the angular diameter distance, and here we are sensitive to physics after recombination. That's the reason why the vast majority of attempts aimed at solving the Hubble tension clustered around these two possibilities: early time new physics before recombination, or late time new physics after recombination. I will now focus on early time solutions, and I will try to convince you that early time solutions can have a huge impact on our understanding of inflation. So what is the philosophy of early time solutions? Well, what we want to do with early time solutions typically is to reduce the value of the sound horizon. If we reduce the value of the sound horizon, then to keep the angular scale of the horizon fixed, we also need to reduce the angular diameter distance from the CMB. And you can do that simply increasing H0. You see from this plot that if you want to shift the constraints on H0 in the direction of what is measured by shoes, you need to reduce the sound horizon. So the question is, how can we reduce the sound horizon? Well, there are two ways if we look at its definition. Either we work on the baryon photon sound speed. You can do that assuming some new interaction between baryon and dark matter, photons and dark matter, and so on and so forth. Or we can try to increase the expansion rate of the universe before recombination. I want to follow this second possibility. I want to check what happens if we increase the expansion rate of the universe before recombination. There are many ways to do so. I will start following a very simple T-model. I will start checking what happens increasing the expansion rate of the universe before recombination by increasing radiation. In the standard model of cosmology, radiation is essentially fixed by the effective number of relativistic degrees of freedom, and effective, which is counting how many relativistic particles we have. And in the standard model of particle physics, essentially we have 3 relativistic particles corresponding to the 3 families of neutrinos, plus an additional correction of 0.04, which is coming from the non-instantaneous neutrino decoupling. However, there are many models that can predict corrections to this value, that here I will parameterize in terms of delta and effective. This is usually referred to as dark radiation. I will remain blind to the specific model that predicts additional dark radiation. I will just check what happens if we increase by hand delta and effective. And in particular, I will check what happens if we increase delta and effective from 0 all the way up to 1, just as a case study, just as a toy model to understand what is happening. So if we start from delta and effective equal to 0, we are in ΛCDM. We have the well-known phi sigma tension with shoes, and we measure the canonical value of the sound horizon. If we start increasing delta and effective, the universe will expand faster before recombination. We can reduce the sound horizon, and if we reduce the sound horizon, we can infer larger values for the Hubble parameters. Eventually, we will be in agreement with shoes. However, the point I want to make is that this has implications for inflation. In particular, you see from the second panel of the figure that in ΛCDM we used to measure NS to be different from 1 at more than 8-point standard deviations. But when we decrease the sound horizon, when we increase H0, we shift the constraints on NS all the way up until to NS equal to 1. On the other hand, the constraints on the tensor amplitude do not change. If we interpret these results in terms of the Slorol parameters epsilon and eta, well, the constraints on epsilon do not change because the tensor amplitude is not changed. On the other hand, the constraints on eta shift from negative values all the way up to 0 or positive values. This calls into question the hierarchy we derived in ΛCDM. And at this point, you may say, okay, but we know that we cannot really solve the Hubble tension with extra dark radiation. How much dark radiation is allowed? Well, this is true. From this figure, you can see that just to reduce the Hubble tension down to 2 sigma, you will need corrections in delta N effective of 0.5. And models that predict delta N effective equal to 0.5 are strongly disfavored over ΛCDM in terms of Bayesian evidence. So we know that this cannot be a compelling solution for the Hubble tension. But the point I want to make is that our constraints on inflationary parameters are much more sensitive to that. In particular, you see that corrections in delta N effective of order of 0.2, 0.3 are already enough to completely change our results in terms of what models of inflation are favored or disfavored by data. And you see that from this figure, models with delta N effective 0.2, 0.3 that are only weakly disfavored compared to ΛCDM and can only reduce the Hubble tension down to 3.5 sigma, well, these models already require a number of e-folds before the end of inflation that is exceeding 70. Therefore, models of inflation, such as Starobinsky, will no longer be supported by data. And I want to show you that this is happening also in highly studied possible solutions of the Hubble tension, such as early dark energy. In early dark energy, we have a de Sitter phase just before recombination. Our universe will expand faster. We can quantify this effect in terms of the fraction of early dark energy that we have in the model. If the fraction of early dark energy is 0, we are in ΛCDM. If the fraction of early dark energy increases, then essentially our universe will expand faster. We can decrease the sound horizon. We decrease the Hubble tension. However, we move towards an S equal to 1 again. And you see that a fraction of early dark energy between say 4% and 6%, which is only able to reduce the Hubble tension down to 4.3 standard deviation, is already enough to change our results on inflation. Because you see, again, that you need a number of e-folds of expansion which is greater than 70. And so models such as Starobinsky are no longer supported by Planck and BICEP data. And in particular, what I've done is to perform a joint analysis of early dark energy Starobinsky inflation, where the two models are simultaneously assumed in the same theoretical picture. And you see from the model, again, that if we fix a background ΛCDM cosmology, if our universe is ΛCDM, then Starobinsky inflation is one of the best fitting models of inflation. But when we consider early dark energy, if we want to reduce, not even solve, just reduce the Hubble tension with early dark energy, then we move towards an S equal to 1, and Starobinsky inflation is no longer supported by Planck and BICEP data, because you will need a number of e-folds which is not allowed in the model. So let me derive my conclusions. There is a widespread consensus in the cosmology community that we attained a robust understanding of inflation, which is of course true, because we measure the spectral index and the tensor amplitude. We have strong constraints on these two parameters. And it seems that Starobinsky inflation and models similar to Starobinsky inflation are the best fitting models given this data. But there are important caveats around these results. First of all, any constraint on inflationary parameters, most importantly the spectral index of scalar modes, are intrinsically model dependent. We need to assume a model of cosmology to extract information about the inflationary parameters. And if we change our model of cosmology, we can change the results on inflationary parameters. And in particular, it seems that early time solutions that try to solve the Hubble tension can imply a substantial shift towards an S equal to 1 or towards larger values of an S. And this has, of course, implications in terms of model selection. A caveat that I didn't have time to discuss is that CMB experiments other than Planck, such as the Atacama Cosmology Telescope, are already favoring larger values of the spectral index, in disagreement with Planck and in disagreement with Starobinsky inflation. And the same experiments are giving preference for early dark energy. What are the possible implications? Well, first of all, if the Hubble tension will be confirmed And if early time solutions will be identified as the way to move forward in the discussion, then it's very plausible that at some point we need to reassess our understanding of inflation and what models are favored, disfavored. But this is too early to say. We need to see what happens for the Hubble tension. This is too premature to say. At the same time, I think it's a bit premature to do robust model selection with this data, because the caveat surrounding our results is that we are assuming ΛCDM. And the question is whether we can trust or not about ΛCDM until we solve the Hubble tension. That's it. Thank you for your attention.
Questions?
Hi, nice talk. So you showed a slide where you were showing the tensor perturbations and scalar perturbations, the strength for different power spectrum in the CMB. So what do you think about the EB cross spectrum?
Well, that depends whether you assume parity as a symmetry of nature. If you assume that parity is conserved in the universe, that spectrum is constrained to be zero. We know that parity is violated by electroweak interactions, for instance. However, as far as I know, there is no compelling signal in that cross spectrum. If turns out there is a non-vanishing signal, then we can extract some information from the spectrum. As far as I know, that's very useful if you want to constrain some mechanism of inflation, such as particle production and stuff like that. But for sure, the easiest way, let's say, to measure primordial gravitational waves will be the BB spectrum at large angular scales, because that's where you are very sensitive to the tensor amplitude.
So if you assume some parity violating physics, then would the EB power spectrum also be able to constrain the tensor?
I think so, but I'm not sure to what extent, because then you are sensitive to many mechanisms, many parity violating mechanisms, and yeah.
Thank you.
Welcome.
Okay, thank you. Yeah, very general questions. What about the slow roll? This is a very good approximation, but in some sense very rough. Can we go beyond slow roll and get some additional folds?
Sure. So the point is that we can for sure go beyond slow roll. We can solve the equation of motions numerically and see what happens to the spectrum, and then do all the analysis exactly without just, you need to assume a model, you integrate the equation of motion, and you have the predictions. To me, I think this is a bit beyond the sensitivity that we currently have, because slow roll inflation is, the slow roll assumptions is precise at percentage level. And I think that when you start changing the cosmological model, the change you produce in the constraints are much larger than the effects you would obtain integrating exactly your equation of motion for inflation.
So as you constrain NF, delta NF with CMB and BICEP Keck array data. So if the delta NF is very large, for example, 1 or is larger than 1, it's very natural to resolve or solve the H0 tension, right?
Well, yeah, but it's not really supported by data, as you can see from this figure here. When delta N effective is too large, the Bayesian evidence is very, very high, which means that the model is strongly disfavored compared to ΛCDM. And essentially what is happening is that the fit to CMB data is worsened by a lot compared to ΛCDM. So if you leave delta N effective free to vary from CMB alone, you get an upper limit of 0.3 that is reflecting exactly this behavior in the Bayesian evidence. If delta N effective is larger than 0.3, then the fit to the CMB data is very poor, and you cannot really consider this model.
So here, the delta NF equals 1 is preferred, right?
No, it's strongly disfavored.
Disfavored?
Yeah, strongly disfavored.
Ah, okay. Maybe I think it depends on your definition for the BS.
Yes, it's defined in such a way that positive values are disfavoring additional corrections in delta N effective. The point I wanted to make with this figure is that you can, in principle, if you increase radiation, you can decrease the sound horizon and go all the way up until you are in agreement with shoes. but you are worsening the fit to CMB data. So you cannot solve the Hubble tension in this way. But models with delta N effective 0.2, 0.3 that are only weakly disfavored over lambda CDM, so the fit is still good, the fit to CMB data, this is already enough to change your results on inflation.
Okay, I have a question which is related to the previous one. Could you avoid adding extra degrees of freedom if you change the shape of the primordial power spectrum? For example, if you have rounding or some other similar forms?
I think you can. I think there are also papers where it was pointed out exactly how you need to change the primordial power spectrum in order to solve the Hubble tension.
So, I mean, is there any way to mimic this behavior without any other shape?
Not really, because I'm assuming a power law. So I'm just assuming that these Laurel predictions hold through, and then just changing the background cosmology to study the implications.
Okay. Quick one. What is the status of the running? Still?
The running? Well, I didn't explicitly check what happens if we have the running. Typically, you can, probably you will end up increasing the running towards positive values that are compensating for higher values of NS, right? You can recast part of the shift in NS to a shift in the running, but typically, Laurel inflation prefers negative runnings, and in this case, you will move towards positive runnings.
Thank you very much.